Hello and welcome. In this tutorial, we will focus on PBPK modeling using GPX. Before this tutorial, you should go through another tutorials, such as how to create project from scratch, physiologies and physiology schedules, ADMET predictor import, and run modes, with special focus on optimization. We will use tobramycin as an example for PBPK modeling. I will take you through input parameters and then we will go to PBPK settings. Tobramycin is highly hydrophilic compound with log P around -5, highly basic with 5 pKa's starting from around 6 and ending around 9. Very soluble and very poorly permeable. You can see that the permeability is very low. Ratio of blood to plasma is predicted to be around 1.5 and fraction unbound in plasma is around 92.5. All these properties are in silico properties, so they were predicted by ADMET predictor version 11. And we will just use these properties for this exercise. Now we will go to our example. Since the example itself is quite lengthy, I pre-created number of assets. So this way we can focus just on the PBPK module. But before we go through example, I wanted to show you the data that we have, so experimental data. So this example involves rat IV bolus data for 16 milligrams per kilogram, one set of data. 3 sets of dog IV data, also IV bolus. So it was 5 milligram per kilogram, 10 milligram per kilogram, and 20 milligram per kilogram. All dogs were 20 kilos in body weight. And 2 sets of human IV data. One was IV bolus, 1 milligram per kilogram body weight, and second was IV infusion, 1.5 milligram per kilogram dose given to a younger subject, 14 years old, with 66 kilogram of body weight. So going back to GPX, as I said, we already have pre-created assets. So when we go to observe data, we have rat, dog, and human IV data. And I group them just into the species type of data. And we have to remember that we have sometimes more than one dose. So for rat, we have just one dose. For human, we have 2 doses. And for dog, we have 3 different doses. Below, I added for each species the experimental data. So you can see that if we look at the rat, we have 1 set of data. If we look at the dog, we have 3 sets of data because they were 3 different doses. And we look at human, we have 2 sets of data. So since we entered the data and underneath we specified the dose amount, infusion type, body mass for each of the species, just to make sure that all the information related to experimental data is here. We can go to the compound. It's where I imported the structure. So here you can find the physical-chemical structure of the compound and physical-chemical properties such as solubility, pKa's, log P, and permeability. We don't have enzyme kinetics or transporter kinetics. As you can imagine, the compound is highly hydrophilic and it won't be metabolized for that reason. There are probably some transporters involved, but we do not have transporter data. We will try to use permeability limited tissues and specific PSTC that represents passive diffusion in and out of the tissues. When it comes to dosing, we have just 2 types of formulations, right? IV bolus and IV infusion. So we entered this here. For dosing schedules, we have to create a schedule for each of the dosing that we consider in these simulations. Now we will go to physiologies. So here, for each of the species, when we create the project from scratch, the software will set up automatically the compartmental PK. If we want to use physiologically based modeling, we will have to create per physiology for each of the species, and the physiology has to be specific to the species weight, and in human also gender and age. So we will start from rat. Our rat is 0.232 kilogram. So I have already created a rat and entered its body weight. So now we have to create per physiology. Click on create per physiology, and we don't have to worry about gastrointestinal part, as I said, because we want to look at the oral absorption. After that, we can go to pharmacokinetics and we can click on PBPKPlus. When you open it for the first time, you will see perfusion limited tissue model. So by default, you should see this kind of diagram of PBPK. And if you want to switch to permeability limited tissue model, you will have to click on this button, permeability limited model. For rat, we created two types of physiologies. I named them separately, even though it's the same rat. I named the first physiology rat 0.232 kilogram, and the second the same name with extension permeability limited. The reason for that is that we want to see first how the simulation with perfusion limited tissue model looks like. Typically, this is the default model that we start PBPK simulation, and we go to permeability limited tissue models only if the perfusion limited tissue model doesn't work. You can see here also this specific PSTC value already. Normally here it would be 0. As I said before, I pre-created already certain assets and optimized this value was one of them. So here I will explain to you how I arrived at this value in the next step after this record. So here for this combination of physiology and the dose, we will leave perfusion limited tissue model. This PSTC is not going to be used. I will check below the tissue types, KPs, clearances, apical PSTC, fraction unbounding tissue, and so on, and volumes, blood flow, and lymph node. So this table gives you all the parameters associated with each of the tissues as calculated based on the physiology and based on the physicochemical properties of the compound. So here, when I click calculate KPs, I will make sure that the KPs are calculated based on the current type of tissue models, which is perfusion limited. Before we had mobility limited model, these PSTCs here were calculated. So I will delete the PSTCs from here. The other thing that shouldn't be here actually is the liver clearance. And the only reason it's here is because I didn't pay attention when I was importing the structure and didn't uncheck the liver clearance. As I told you before, the predictions are sometimes not perfect for structure-based predictions. And for this compound, we wouldn't expect any liver clearance. So for that reason, even though there was predicted some liver clearance, I deleted it here and left only kidney clearance, which during the structure import was set up to the standard default method FUP times GFR, fractional bounding plasma times glomerular filtration. So it's passive renal filtration only. So once we adjusted the clearances and deleted the leftovers from permeability limited tissue model, we can take a look here underneath the table. So here, if you click on these arrows, you will see the methods of KP calculation and FUT calculation for perfusion limited tissues and for permeability limited tissues. These methods are set as default methods. If you want to go to some other methods, you have them here. For fraction unbounding tissue calculation, you will find 3 methods KP based. Lukacheva version 1 is the latest method and it's our default method. There are a little bit different settings or default settings for permeability limited tissues. So Poulan extracellular is the default KP method, and for intracellular concentrations, we use the same Lukaceva version 1 method. Again, if you click on any of these arrows, you will have choice of other methods. When it comes to permeability limited tissues, we don't advise changing from the default method from extracellular concentrations, and you could pick from different. This is Lukaceva version 2 is the older method that you could choose here to calculate intracellular concentrations. Underneath this table, you will see steady state volume distribution. So this is the volume distribution calculated based on the method and KPs, and the systemic clearance, which is some of the clearances that you see in this column. Nowadays, also half-time is being calculated. Just maybe to show you again where you will find the tissue-specific parameters. So these are general physiology parameters that you will find here. Obviously, we don't have any enzymes and transporters for this example, so we will leave it as it is. And let's say if we click on one of the tissues, so let's look at kidney. You can see the kidney-specific parameters, and here you can choose the method of kidney clearance. So by default, we use FUP times GFR, but you have also the other clearance. Maybe one more thing, the advanced options, which we typically do not touch, but if you are very advanced PBPK modeler, you could also tinker with the advanced option. Typically, we don't advise to change this option. So once we are happy with our settings, we can now save it for make sure that all the changes have been taken into account. And now we can go to simulations. So in simulations, it's where we put together all the assets, right? So here we have the dose and the physiology and physiology schedule. And now we have to change the pharmacokinetic model from compartmental to physiologically based. And we get these warnings here, which we have changed the model, and we have warning about paracellular permeability, which is at the moment not important. So once I set up everything for this record, for this simulation, I can now run simulation to check if everything looks okay. So as you can see, there is really not a good match with perfusion limited tissue model. And for this reason, we know that permeability limited tissue model is probably better choice. So we will go now back to rat, and we will use the second record, which is for the same data. We just named this record permeability limited to see the difference between perfusion and permeability limited tissue model on the same plot later on. So again, we go to population estimates for age-related physiology. We'll create physiology for the same rat. We will go to pharmacokinetics. And here we already have, as I said, software remembers the previous run. So let's revert it to the situation. It should be similarly to the previous example. We should have by default perfusion limited tissue model, and we shouldn't have any PSTC. PSTC is permeability surface area product, which is multiplied by the surface area of each cell. It's something that is part of advanced PPK training, and we will not focus on that aspect here. But this one number can be used to calculate passive diffusion into each cell based on the cell surface area, as I said. If you have already IV data like we have for preclinical species, and we, based on the physicochemical properties of the compound and the shape of IV profile, we have some idea that perfusion limited tissue model should be used. We can optimize this parameter. I have optimized this parameter starting with some guessed value, and the final iteration gave us this 4.54 times e to minus 5. So that's why you see this value here. So now I will switch to permeability limited tissue model, and will click here to use specific PSTC. I'm telling software to use this optimized number. Also, I will calculate KPs, and again I will delete 0 for liver clearance. And so perfusion permeability limited tissue model, these parameters are being used here. Steady state volume distribution is calculated again here, and it's a little bit different. And you can also see the systemic clearance calculated here and half time. So we can save now these changes. And we can check in physiology schedule that everything is all right, and then we can go to simulations now. So we have to look at the combination of the simulation, which is for this simulation should have permeability limited extension. The dose obviously is the same. We have only one rat, and here initially when we switch it should be compartmental model, and we should switch to physiologically based. So here we have these warnings. We can telling us that we have changed or made all these changes. We can click on done and save project. Now we can run simulation just for this record to see how it looks like, and we can see that definitely now we have really good match between the observed and simulated data, which means that this permeability limited tissue model and specific PSTC works very well for this compound. So in the next stage, what we will try to do is to use this optimized PSTC against rat data and apply it to dog to validate that indeed the combination of permeability limited tissues with the optimized specific PSTC against rat data works also in the dog. If it happens, then we can use the same PSTC and permeability limited tissue model for human to predict human IV data. So let's see if it works. So now we will go again to physiologies, and now I will choose dog. Now we'll click on create per physiology. Subsequently, we will go to pharmacokinetics, PBPKPlus. Based on the rat example, you should already know if you start from scratch, you should have here perfusion limited tissue models. So you should switch to permeability limited and enter the same specific PSTC that we optimized for rat. And here's turn this usage of specific PSTC by moving this dial right to the right. And then calculate KPs, liver clearance, which I will 0. And I will use default gastro method for calculation of these KPs and fraction unbound in plasma. This is my volume distribution for dog, and this is the systemic clearance. Now we can go again to physiology schedules, and here we will pick the dog schedule, go to simulations, choose dog, and now we will switch from compartmental to physiologically based model and save it. Now we will do the same for 10 milligram dose, save it, and 20 milligram dose and save it. So we can run simulation for, let's say we can start with the lowest dose. So we can see this is the lowest dose data. It matches pretty well. And we can do it one by one, or we could later, when we go to runs, I can show you how to run all three at the same time. So we can, from this exercise, we can learn that indeed the permeability limited tissue model and PSTC, specific PSTC optimized against the rat IV data is also working for the dog data. So we can try to predict human. So let's go again to physiologies and find human. Let's pick the first grown-up human. So I already set up the information for this subject. So now I will create per physiology for this subject. And then we will go to pharmacokinetics. And here I will switch to permeability limited tissue model and enter the rat PSTC, which was 4554 E2 minus 5. And then I will click here to use this specific PSTC. Now I will click on calculate KPs, and from here, see that we don't have this liver clearance. So I'm just checking that there is nothing to worry about. Obviously, if you had liver clearance and you wanted to add linear clearance, you would add it here. Or if you had enzymes involved in the metabolism or transporters, you would add them in these tables. So now I can save this physiology, and I will go to physiology schedules, choose this human, go to simulations, and this was 1 milligram per kilogram human. So here I will switch to from compartmental to physiologically based mode and save this option. And here I can check that, yes, I accept all these changes. And let's see, let's run simulation for, this was IV bolus. So, it's not perfect, but it's a pretty close considering that it's pure prediction. So let's go now to the other IV infusion data, which was for this younger human, 14 years old, 66 kilogram. Let's create per physiology for this subject. Go to PBPKPlus, and again, I will go to permeability limited tissues. We will enter 4.544 into -5 PS specific PSTC and turn on use specific PSTC. We will calculate KPs. And here I'm checking again if I don't have this liver clearance, and I don't, so it's all good. This is volume distribution and systemic clearance for this subject and the half time. So done, and I will save these settings. So now we'll go to physiology schedule and pick the younger subject, check if everything looks okay here, go to simulations and also pick the subject. So the subject was given IV infusion 1.5 milligram per kilogram body weight. So here we have to switch from compartmental to physiologically based, and this way we have all done. Maybe on the other note, before we run simulations, you should pay attention what simulation length you should set up for each of the species, because each data were gathered over different period of time. For that reason, you might pay attention to the simulation length, and so you would set it up here. Also, you can change output frequency to have smoother lines, so you would change it to every 2 steps, and sometimes you have to change mass balance tolerance if you have noisy line, but most of the time it should be okay. Okay, so now we can run simulation for this subject separately and can see how it looks like. So yeah, we can see it's a little bit under prediction of the Cmax, but overall, as considering its first in human prediction, just based on in silico data, right, and optimized PSTC, it's very good prediction. So I wanted to show you only other things. So the runs. In runs, you can set all kinds of combinations, so run names. So on the left side, you can actually put every simulation that you run here. Also, I have here the optimization because I optimized this PSTC, and also I've done parameter sensitivity analysis before that. So you can see these run names here. So all the runs that I created are here. On the right side, you have again the simulation names, but here you can group the simulations. So for example, if I want to show all the dogs in the same plot, I would choose dog all and I select all 3 doses. And now I can just run the simulation for all 3 dogs at the same time. So you can see I can create a plot with just for the dog with all the doses, and that's where I would stop. I think you should get some good preview of how to use PBPK modeling in GPX. And if you have any other questions, here is the contact information. Thank you.